coat already applied. Athens machines its smaller, higher volume frames on a continuous transfer line process. Multiple machining operations are done on a continuous basis, increasing productivity. All frames are washed after machining to remove any metal shavings that could damage the insides of a motor. Larger cast iron frames are machined in a state-of-the-art automated machining center. This fully automated machine efficiently completes all of the precision machining steps required per the motor's design. The cleaned, finished frame is ready to be moved to assembly. Cast iron end plates are supplied to Baldor already primed and ready for precision machining. Baldor uses specialized silicone steel for its laminations that reduce electrical losses and increase motor efficiency. The coil spools are unwound into a press that straightens the steel to the necessary flatness for stamping. Finished rotor and stator laminations are punched from the same piece of steel. All waste metal is recycled. Heat treatment of the finished stamped laminations is required to relieve stress in the steel. This process improves the electrical and mechanical performance of the parts. Computerized quality control inspections confirm that exact design tolerances are being met during the manufacturing process. Stator laminations are stacked to the required design height and loaded into an automatic welding machine. The welder compresses the stack uniformly to minimize distortion while welding it together into one piece. The lamination stack begins the stator winding process by having slot liners inserted. These insulation liners will protect the copper wire coils from being damaged by the lamination steel. Automated coil winding equipment is used to form coil groups. Finished coil groups are transferred to an automatic insertion machine that uses precision alignment to carefully insert the coils into the lined stator slots. Phase paper insulation is inserted in between coil layers on both ends of the winding. Proper insulation placement is important to ensure the long life of a motor winding. Coils are connected per the electrical design requirements. A careful brazing process makes the connection secure. Lacing is added to increase the mechanical strength of the winding. This will prevent vibration and movement of the coils during motor starting and operation. All finished stator coils undergo a computer-automated electrical test before leaving the winding area. This ensures no components were damaged during assembly. The coils were connected as the design required, and that the performance of the stator coil meets acceptable design parameters for the part. Varnish is applied to the stator, coating the coils and other insulation materials. When dry, the stator becomes a solid unit, preventing coil vibration and movement. Stock motor designs use a dip and bake varnish process. Athens also offers a vacuum pressure impregnation process on custom designs. The stator is now ready for insertion into the motor frame. Smaller size motors have the stator pressed into the frame. During this process, the motor leads are carefully fed through the outlet hole in the frame. Larger frame designs are assembled by heating the frame so that it momentarily expands just enough to allow the stator to drop in. Once inserted, the stator is welded to the frame to prevent movement. Rotor laminations are stacked on a casting pin that controls skew angle and concentricity of the lamination stack. The laminations are pressed to prevent distortion during casting that could damage the coating on the steel. The casting machine precisely controls the injection of the molten aluminum from the bottom up into the rotor stack, eliminating porosity in the casting. Each cast rotor is final inspected before it is given a mark of approval by the operator. The keyed shaft is pressed into the cast rotor to create a complete rotating shaft assembly. On NEMA 440 frames and larger, the shaft is permanently welded to the rotor to prevent any movement. After assembly, the shaft is checked for proper runout before it can move on to final machining. The shaft is now ready for machining to its final dimensions. Computer-controlled machining is used to achieve the proper air gap tolerance. The shaft is dynamically balanced to exact specifications. This improves motor life due to less vibration of the rotating assembly and bearings during motor operation. Severe duty motors get an epoxy protective rotor coating for harsh environments. Bearings are expanded by induction heating and slid onto the motor shaft. They are temporarily wrapped during final assembly to prevent contamination. All parts needed for final assembly are collected together on trays and delivered to the assembly station, where they are carefully assembled into the completed motor. Impro seal bearing isolators are installed as standard on both ends of IEEE 841 motors used in petroleum processing applications. Mounting flanges on large frames are machined again after final assembly to ensure the flange face is true to the motor shaft. Each motor is given a routine test after final assembly to ensure the assembled motor will perform to design requirements. Custom testing is also available in the Athens Test Lab, where witnessed and unwitnessed full-load dynamometer testing is one of many testing services available on request. Motors are painted to their specification with epoxy or lacquer finish. Shipping pallets are built to size, providing sturdy support and protection of stock and custom motors during shipment. All motors are securely fastened to the pallet. Testing includes 6 different procedures that involve elongation, bending, and baking the magnet wire. These tests help to nurture both supplier excellence and product quality. High voltage testing is done to be sure the windings will withstand voltage surges. All test data is downloaded into the plant's Infinity SPC database to establish conformance and long-term process controls. Copper rotor bar concentricity is critical to eliminating the sources of motor vibration. Here, measurements gauge concentricity from top to bottom and side to side throughout the length of the bar. Lamination steel used in the stator plays a key role in maintaining consistent and efficient electrical performance. The Epstein and Franklin tests shown here measure the chemical, physical, and insulating properties of our lamination steel. Shaft machining begins with a steel blank. Then all the surfaces and shoulders are turned in a single process. Next, we mill the keyway and drill the centering holes at the end of the shaft. Because low vibration and bearing life are so important to customers with critical service applications, we finish grind the entire length of the shaft, including the rotor core, where a perfect fit with the shaft is essential to keeping motor vibration in check. Making laminations begins with punching the stator and rotor blanks. Precise stator lamination geometry is the key to optimizing heat transfer inside the motor. With slot notching, we also get a clean edge in order to avoid damage to the magnet wire during the winding process. By notching rotor laminations, we are able to maintain extremely tight tolerances. Notching also makes it easier and faster to adjust slot configurations and facilitate rapid design changes. All finished laminations go through a quality check of the dimensional consistency between laminations. Heated laminations cool and shrink on the arbor. Then the stack is compressed from top to bottom. In the die caster, molten aluminum enters the core from the bottom. This forces air out through the top and prevents rotor porosity. As the core is removed from the arbor, notice the vent holes at the top. This honing process yields a perfectly sized and round bore. We typically hone the bore for motors and applications where low vibration is required. After honing, the rotor core is heated and expanded before we insert the shaft. For ultra-precision balanced motors, gradually cooling the rotors relieves stresses and reduces vibration. The assembled rotor and shaft is now balanced. Our loose-fit rotor bars are not restricted and are able to maintain their geometry as they heat up. Next, bars are brazed to the end rings with an exclusive process that prevents warpage and bar breakage. The turning lathe shown here trues up the end rings and brings them to the proper size. Prior to vibration testing, the assembly is given a protective coating. This slow roll procedure checks mechanical and electrical shaft runout. Just like the rotor cores, precision and concentricity are critical to building high-quality stator cores. To ensure a tight fit between laminations, the core is compressed and welded straps are applied. Applying Lean and Six Sigma to our coil cell reduced cycle time from 21 days to 7.5 hours. All the key processes in this cell, such as winding, shaping, and insulating, are computer controlled. This coil winder, for example, maintains constant tension on the wire as the coil diameter builds. With this kind of precision, we can be confident that all completed coils are exactly alike. Robotically taping the magnet wire periphery puts repeatable precision where you need it most. During taping, insulation tension and the critical insulation overlaps are tightly held to exacting specifications. Standard practice for making form-wound coils often involves a lot of arm wrestling and hammering that yields dissimilar parts. This is no longer an issue with our computer-controlled capabilities. Here, the engineer indirectly controls every step of this spreading and shaping process. Slot lining and insulation paper make it easier to insert the coils without damaging the coil tape. Here you get the feel for what it takes to get the coils properly located. Our loop connection for sealed insulation systems will seal off the lead connections, making it impossible for moisture to reach this important junction. Before going to varnish, the stator gets a surge test to ensure coil integrity. We also high pot the windings to ground as a final check before varnish. Begins with the oil rings. Once the edges of the bearing hub are trimmed, the bearing halves are mounted. Here, key components such as the bore, rabbet fits, and seals are measured against design tolerances. The anti-friction bearing you see here is being prepped for assembly. Here, the sleeve bearing assembly is mounted to the motor frame. Next, the anti-friction bearing is mounted. Followed by the fan. And the fan cover. Kings Mountain can do full load dyne testing up to 4,500 horsepower and 7,200 volts. In order to isolate this motor during vibration testing, note that it is bolted to a seismic mass. During the paint process, quality is still the priority because we know paint durability and appearance are important to our customers. Now, as we take a look at a few products, you will see some of the craftsmanship put into every motor built in this plant. This is a TEFC motor with a low noise fan cover. This TEFC motor has sleeve bearings and an auxiliary blower. This 9500 frame weather protected motor is a typical critical service design for the petroleum industry. This shows a customer's half coupling and several